Welcome to lecture 15, which is on Sted, which is short for stimulated emission depletion microscopy. Sted is a confocal imaging technique. It's again a super resolution imaging method. So it does provide images that have better resolution than lambda over 2 Na. The technique earned Professor Stefan Hell from Göttingen his Nobel Prize in 2014, interestingly in chemistry. And it is a technique where Stefan Hell actually says what he's done, he has engineered the point spread function in such a way that the imaging resolution is lower than lambda over 2 Na. And you may wonder, is it physically possible to get a PSF that is smaller in width than lambda over 2 Na? No, not directly. Of course, that would be breaking Abbe's theory. But through a physical trick, you are able to make use of this point spread engineering to generate an excitation spot that in fact is smaller than lambda over 2 Na. And I will show you how that works. So the key thing to take home from today's lecture is that in Sted microscopy, the resolution is dependent on the laser intensity that you use to excite your sample. And so we will go into this and you will see why that is the case. So the higher the intensity in the Sted laser, the higher the resolution that is theoretically achievable. So let's just begin, because I said it's a confocal technique. So I'll go to my paper visualizer now, and let's just see how this works, this technique. So let's review first of all again what a confocal microscope does. And so in a confocal microscope, what you have is you have a sample point, and the fluorescence from the sample is collected. It travels through the objective lens, and then it goes through the tube lens, and is then imaged onto a pinhole. And we said the pinhole is there to reject out of focus light. So let's just draw this. This is the pinhole. And so here are my two lenses. Here's the objective lens, and here's the tube lens. And the way that you do this is you have a beam splitter here, and the beam splitter, it accepts light from a laser, and the laser is then thrown onto the sample. It's focused onto the sample. So it's shown here in blue, so the laser goes up in blue. So here is the laser. It is focused through the objective, so this acts like the condenser, as a condenser, but also as the collection objective. So the fluorescence shown then in red, the Stokes shifted fluorescence, travels through the beam splitter, is focused onto the pinhole, and then goes on to the detector. And as usual, I draw the detector by just making sort of an eye, but usually this will be a photomultiplier tube, as it is called, or a photodiode. The sample is here. And so what resolution do you get in this microscope? Well, this objective here will focus the laser spot onto the sample plane X, Y. And of course, I mean, if I just turn this around, the sample spot will be a diffraction pattern, the PSF, and it will have size lambda over 2 Na, of course, right? And so the resolution you can get from this excitation is never going to be better than lambda over 2 Na. So let's suppose I excite a fluorophore with this point. Of course, I scan the point across the sample. Then the intensity at the sample plane at the image plane. In this case, the image plane is the confocal plane. And remember, sample and pinhole plane are conjugate. They are confocal with one another. Then the intensity I at x dashed y dashed is equal, or it is proportional to the PSF excitation, which is this function here, convolved with the fluorophore distribution in the sample I of x, y. So the point is, of course, that in confocal imaging, you raster this point across the sample and you record the intensity as a function of time. And so the time trace then you scan across the sample and you get what is called an optical section from a certain plane that is in focus with the pinhole. So it's this optical sectioning capability that improves contrast in confocal, as we've described in earlier lectures. However, the PSF of the excitation is lambda over 2Na, and so it is between 2 and 300 nanometers as usual. So it is normal diffraction limited. So how does the Sted principle now work? Now let's, for this, go quickly to my presentation. So if I go to my presentation here, let's just do that. Then you see that here you see the rastering principle on the right-hand side. You scan the excitation PSF across the sample, and then you move the sample in Z to get different planes, and so you raster essentially the sample in different planes, and you can regenerate a volume. So here, focusing the laser spot will give you lambda over 2Na as the diffraction limited spot for excitation. And so here you have the formula that I've just shown you. The intensity, so if I put on my laser pointer, the intensity in the image plane, I of x dashed y dashed, is proportional to the excitation PSF, shown here as this green excitation blob, convolved with the fluorophore distribution in your sample. So here you see a sample, the letters LAG, as shown here as a cartoon, with fluorescent molecules, decorated with these fluorescent molecules. You scan the laser beam across and record the signal. And you can now see within one PSF, if you have a small sample, you will excite lots of molecules. And that gives rise to image blur. So the actual image that you get will be blurred and look like something like this. Okay, so as I said before, it's like drawing an object with a blunt pencil. If you don't have a sharp pencil, then you don't get the smallest features accurately reproduced. And so with normal confocal imaging, the bluntness of the tip is lambda over 2Na, about 200 to 300 nanometers. How does then stimulated emission depletion work? And so I would like to show you the principle of that as follows. So why don't we go back to the visualizer to show this. So I'm now here back on the paper. So the principle of Sted, or stimulated emission depletion, is as follows. So what you do is, if you have your excitation PSF to look like this, so it's a Bessel function squared, PSF excitation, you put another beam onto the sample that is aligned and has a very funny profile. It has a profile in 1D that looks like this. I wanted to take a red color here to do this. So here's the red color. So you can see that this so-called Sted PSF is a beam that has a 0 at the center. So where the excitation beam that we showed up here has its maximum, you arrange this beam to have this funny shape, to have a 0 in the center. How we will do that, I'll explain to you later. But it has a high intensity in the wings, right? So in these two lobes, which is on the outside of that excitation PSF. Let's just accept that for a moment. So this is a cross section through the beam. So of course, the central beam is just our Bessel function. It's normal PSF. It's a round circular thing, and then the Sted PSF actually has this profile, which in 2D is a donut. It has this donut profile. I'll show you that on a picture later on. But the idea of this Sted beam is to deplete signal from the wings of this excitation PSF. So wherever this the intensity of this Sted beam is high, you switch the signal off. How do we do that? I will explain that in just a minute, how we achieve that that switch off behavior. But for the moment, let's suppose blue switches on and red switches off. What would the overall fluorescence signal be? In fact, what this yields is a suppression of fluorescence, and the suppression factor is given by a function called eta, and eta is of course proportional to the Sted PSF. So we can write the signal in this current case now. It's the same as we had before, same as we had up here. I of x dashed y dashed is now proportional to the excitation PSF times the suppression factor, which is proportional to the Sted PSF. And that whole thing is, as before, convolved with the fluorophore distribution in the sample plane, I of xy. So image is now, it's the same as this, except we have that red depletion factor now sitting on top of this function. Okay? So let's go back to the presentation. And how do we then, how do we switch off fluorescence? Well, in fact, you already know how to do that. If you remember, in our discussion on fluorescence, we have different rates. We have a rate going up, we have a rate going down because of stimulated emission. And of course, we have a fluorescence rate going down plus the quenching rate. And one way of preventing the A21 to dominate is by switching B21 and make it very, very strong. So if you stimulate the emission down as soon as it arrives up there, then you get a stimulated emission photon exactly along the laser beam. But it is not a fluorescence photon. And so the key now instead is to stimulate down using a color that is different to the excitation color. So let's have a look at this. The cartoon of this is shown on this picture here. So we have the normal excitation PSF shown in blue. The Sted PSF is shown here in orange. And you see it has this donut shape with a 0 in the middle. Let's see later on how we generate such a PSF. I will show you that in a minute. And the effective PSF now becomes much smaller than the standard confocal excitation PSF shown on the left here, because in the wings of the excitation PSF, the Sted PSF switches the fluorophore off. It depletes it down. It depletes the population without there being a chance of a signal photon coming back by spontaneous emission. Only where the depletion energy is 0 do you get appreciable fluorescence. And you can actually get the effective PSF down to perhaps 20 nanometers. That's quite hard to do. You need a high laser intensity to do that, very high laser intensity, but 40 nanometers is quite possible to do. So effectively what you've done is you've sharpened the pencil by switching on, with this PSF, with the Sted PSF, with which you are painting the object. And so you see this here now. So we go back to that same picture. We have excitation PSF times the fluorescence suppression factor, which is proportional to this red donut beam, convolved with the distribution of the fluorophores. And so you can now see that actually only a small part of the excitation region remains. And so we are, in fact, suppressing fluorescence, let's say, from these molecules down here, shown down here. And that means that you have a smaller number switched on at any one time, and you get a higher resolution as a result of it. So you're drawing this with a finer pencil. If we now look at how to implement that in practice, so the actual way of doing this is shown on this slide here. So we have our normal excitation beam. Now the picture is the same as I've drawn it on my paper before, except here the sample is on the right-hand side and the detector is on the left-hand side. So it's just flipped around, but otherwise it's the same thing. So we pass the excitation laser onto the sample and the fluorescence hits the detector. So that would just give you the normal PSF distribution for the excitation. But then what you do is you switch on the depletion beam, and the way that you generate the donut is by putting what's called a faceplate into the Sted beam, this red Sted beam. I will show you in a minute what that is, that faceplate, why it works. That generates the donut beam. It is aligned to go exactly around the excitation PSF. So that's really, really important to align that very, very well. They need to be exactly on the same axis. Otherwise, this technique doesn't work very well. And so then you see down here, if we now switch on the power in that Sted beam, fluorescence is suppressed. And in this cartoon, what I wanted to show you is, as we increase the power in the Sted laser from 0 to 9 gigawatts per square centimeter, the fluorescence is suppressed in the donut by this factor here. You can see you can really turn it down to 0. And you have a look at this now, this cartoon. We're bringing the intensity up and up and up and up and up, and you can see the fluorescence point is sharpened accordingly. So let's just do that again. The simulation shows you how much of the fluorescence you're suppressing, so you're getting much less of the green remaining in the center, and so the actual tip you have is sharpened appreciably by an appreciable amount. Note that these units down here, gigawatts per square centimeter, that is not a spelling mistake or a typo. It's, this means 10 to the 9 watts per square centimeter. That is a tremendous power, and that is part of the problem of the technique. The resolution is gained by turning on this depletion laser. If you think about the two-level system, B21 needs to be really dominating, right, for all the other loss rates to become negligible, right? And so this can be detrimental to your samples, and for live biological samples, they don't survive the technique for very long. On the other hand, the signal you get it's just like a normal confocal microscope. The signal you record is the super resolved signal. You need no further image post-processing or anything like that as you did in STORM or single molecule localization microscopy. You get the super resolution just like that. You're simply drawing with a sharper pencil, so to speak. So down here on the left is the is the transition diagram to explain to you how the technique works. So the green beam here leads to absorption from the ground state to the excited state. Then you have rapid vibrational relaxation, and then fluorescence comes down from this lowest level up here to some of these levels down there. And then what you do is you take the depletion laser to go from this lowest state here to match one of the transitions, and this transition is red shifted to the fluorescence. So what you do is you tune your depletion laser to one of the allowed transitions that go back down, but you make sure it is quite red shifted to the fluorescence emission. And my question to you is, why do you do that? So I tell you what one tries to achieve, and then you try and think of why one arranges the experiment like that. So we have a green photon, then you get the red-shifted fluorescence, and the stimulated emission is even further red-shifted away from these two excitation lasers. So in practice, what we have is perhaps we have our normal confocal microscope. You have a mirror that here scans the laser beam across the sample. So the laser beam goes through a collimator here. So you have a parallel beam coming out. You put it onto the objective, which acts as the condenser. Condenser focuses it onto the sample, and by tilting this mirror here, it's essentially you have a mechanical mirror that moves in X and Y very quickly, and that allows you to raster the beam across the sample. And then the fluorescence comes back. So like so, you take the fluorescence back, it goes through this beam splitter here and is detected. So perhaps the laser is at 640 nanometers to excite, and the fluorescence comes back redshifted between 660 and 720 nanometers. And then what you do next is you put your depletion laser on, you put your phase mask into the beam to generate the donut, and the donut goes on top of the excitation PSF. It's a bit unfortunate the way I've drawn here, because it looks as if the intensity is highest. In the middle, it's the opposite. Where it's red, it should be the lowest, and actually the most intensity should be on the outside. So it's a donut beam, that depletion laser. And then you switch that on, and so this is the result of it. So if I go back, have a look, and now I switch the depletion laser in like that, and I line this very, very, very carefully so that you really have the same optical axis. By carefully, I mean really an alignment to the nanometer scales. It has to be very, very precise. So how do I generate this donut? And to do that, I would like to go back to my paper projector. So here is the idea of PSF engineering. So if I just for a moment go back and think of how a lens works. So if I have my objective lens like that, and I have my laser. Let's say I have two rays coming on to my sample that I'm illuminating here. So this one comes this way, and that one comes that way. And then if this is a plane wave, like so, then of course they arrive at that point exactly in phase. I mean, that's the point of a lens. That's exactly what it does. So if I draw this here like so, 4, and this one here is 1, 2, 3, 4. You can see they are exactly in phase at that point. Now think what happens if I put a little phase retarder in part of the beam. So if I put it into this half of the beam, and let's make that phase retarder, so this could be for example, a glass plate. Why is a glass plate like this a phase retarder? Well, it is because it has a different refractive index. It's higher, so that will slow down the light, the wavelengths will squash together, and therefore, whilst the frequency stays the same, and so the phase, the extra phase that this picks up is 2 pi over lambda times delta x times n. 2 pi n over lambda times delta x is the extra phase, is phase change through glass. And so, of course, in this part goes through air, so it would be 2 pi times lambda delta x, where n is equal to 1. For the glass, it would be 1.3. So the difference would be 2 pi 1.3 minus 1 over lambda times delta x in terms of a phase difference between this beam and that beam. And the point about Sted is, perhaps you take a glass plate that is almost the same, except it is slightly thicker on the top than it is down below. And you arrange this glass plate so that the phase change you get between this beam here and that beam there is exactly pi. And if it's pi, then they're out of phase when they arrive here, and you get 0. You get destructive interference as a result of it. So let me show you this now. If I go back to my presentation. So on the PowerPoint, you see that is on. It's on my PowerPoint slide. So good. So you have here one such phase plate. So this is shown here as a circular device that you put in the Sted beam. So if it had a shape like this, so between here, this side of the faceplate and that side of the faceplate, so maybe this is the white part and this is the black part down there, so it is arranged so that there's exactly pi phase difference. And what that of course means is that you get a 0 because light from that side and light from that side will exactly be out of phase by pi and therefore interfere destructively, right? And then therefore you just get this double-lobed structure. And now to make a donut, so this would just make this sort of a 2-lobed structure in 1D because it's only a 1D device. But you can make the donut, the circular shape, by having a face plate where the phase varies as a function of angle radially. It varies as a function of angle going from here all the way around to 2 pi. It varies from here to there by 2 pi. And I want to ask you, so be very careful what you see here. I'll just explain that again, and then you think about it and you work out yourself why this works. So from here to there, there's a pi phase change, and actually from here going all the way across in this angle, as you go across, it goes from 0 to 2 pi, okay, the phase. So why does this faceplate, when you focus a laser beam through a lens like that, generate a donut like that? That's symmetric in X and Y. So if you think about that, if you know how this thing here works, then you also know how this thing works and why you get that donut. So it's a very simple device. You just have to align it very accurately so that the donut, the 0 in the middle, sits exactly above the peak of the excitation PSF. So here you see what happens. You drive population up, and then you drive the population down with spontaneous emission, and then what you get is an effective excitation region that is exactly what we had before, lambda over 2Na. But this lambda over 2Na is now modified by the suppression factor 1 over 1 plus I over I sat, where I sat is let me see, let me just turn this off. Where I sat is the saturation intensity. So it's essentially how simply can we drive the population back down. You you can see, therefore, if I make the intensity I much greater than the saturation intensity, then this factor here, this improvement factor, can theoretically go up to infinity, right? And sorry, I meant in fact that the improvement factor reduces delta EX to 0, right? Because I over I sat goes to infinity. So you see this here for certain powers. You see if you have 200 times the saturation intensity, you get that green thing in the middle. If you have 50 times the saturation intensity, it's somewhere, it's between those two. And at 10 times ISAT, you get an improvement, but it's not as large. And so this is the crux of the technique, putting the power in to drive the transition down. That's the key behind it. So let me just show this. What this means in practice. One can, this is from our own laboratory, you can see what kind of improvements we get. So if we change the power and increase it like such, then you can see going, this is our own work. We've taken some very small beads that have a few nanometers in width. Perhaps they have a 50 nanometer diameter, these little beads. They're decorated with fluorophores. And so if I image them in a normal confocal microscope, I see the beads appearing in the confocal image like this, and each one has a size of 250 nanometers or so, right? As you would expect with a normal PSF. So here's the normal confocal PSF. And then if I switch the Sted beam on, you see at about 6-7 gigawatts per square centimeter, then the beads become much more clearly resolved. You get much smaller sizes for them. Then you can see, for example, that this dot here was not one bead, but it was 2 beads. Or this dot here was actually 4 beads that weren't resolved before because their PSFs were overlapping. So you're turning images that looked like that before into images that look like this. The only problem is the power, and if you do biological samples, then live samples don't like it. So STORM, or single molecule localization microscopy, the previous technique, instead, STORM is too slow, so you have to fix the sample, so it's for dead samples. Sted, you can, under some circumstances, operate it with live samples, but usually after a few images the sample dies because you have a high power that you put on. Nevertheless, you can get incredibly improved images. I mean, so you see here, for example, the so-called nuclear pore complex, which is in the envelope of the nucleus, little units through which material can pass between the nucleus and the cytosol inside the cell. And with a standard confocal microscope, this is what you would see. And with Sted, you can actually resolve the protein complexes on the outside and the inside. You can clearly resolve the complex and its circular structure. The other thing that you can do is you can look at dendritic spines like such, and these dendritic spines are essentially this is the area. This is a neuron that has these protrusions on the side through which the neuron is signaling from one to another. So you get these beautiful images. And in fact, this is done in a live cell. So this is from Stefan Hell himself, who is still the person who does the most impressive research on Sted to this day. But to use it for live application is very, very challenging. So again, to come back, the major advantages are it allows you to image dynamically, also at depth, but a good resolution requires very high powers. So it works quite well at depth 30 micrometers depth is possible, which for a super resolution technique is very good. It is probably of all techniques the one that works best at depth compared to the others. As long as the donut stays well behaved, if the sample is very scattering or something like that else and distorts the donut, then of course the resolution suffers. You need to have a very precise round donuts. So in well behaved samples you can go down to 30 microns. That is certainly deeper than what you could do easily with single molecule localization microscopy. It is possible under some circumstances, and it is certainly much deeper than the next technique, the last technique that I will talk about in this lecture course, which is called structured illumination microscopy. So it's good for sort of tissue slices that are fixed and are labeled with good Sted compatible dyes. The compatibility with biology is often difficult, as I mentioned. And the speed is faster than the previous techniques, so some live imaging may be possible, but it is not as fast as the next technique that I'll talk about. And I should mention, and again, there's this work that Stefan Hell is pushing very hard in his research group, that it doesn't really matter whether you use stimulated emission to deplete the upper state. All you need is a distinguishable state. So you need to just be able to distinguish the excitation state with the emission state. If you can do that very clearly, if you have some other mechanisms of switching the fluorescence, you could switch the color, you could switch the intensity in other ways than you do with depletion. That is all possible. You would still get the same physical principle as you have instead. And so there are some ideas now to actually reduce the power requirement. So if you don't have to use stimulated emission depletion, then perhaps there are other methods that require you to use less power in the depletion beam. So because you're switching some other molecular property, color or something else, right? You can think of all kinds of variations. As long as you have a physically distinguishable state in the donut for the molecules you excite, this principle applies. And so actually, the idea behind this is quite ingenious. So what you do is you don't break the diffraction limit in that sense. You just find a way to not be limited by it in the standard imaging way by using this physical state switching. So here we go. It's these three guys who won the Nobel Prizes for these two techniques I've described. As I said, Betzig and Mörner won it for single molecule localization microscopy. Mörner paved the way because he was the first one to be able to see single molecules on cameras, which of course was a requirement for single molecule localization microscopy. And Mörner for coming up with this idea that actually by switching on and off these individual molecules, I can differentiate them in time. And if I can differentiate them in time, I can spatially separate them because I can fit the point spread function very well. And Hell, in the middle, he came up with the stimulated emission depletion concept. And so, in a way, you're doing the same thing. You're switching off as much as you can and just look and just keep the signal from a very small part. And I urge you again to think back to the first slide. I told you in the beginning, in the first lecture, perhaps it's worth going back to the first lecture again and think through those concepts, because there is a corollary here with the concept from Golgi, who was able to see the neurons. He saw some neurons very, very well because he suppressed all the others with his black reaction. And so all super resolution methods work by this principle of you concentrating on some things to see those with high contrast and resolution by suppressing all the others. That's key to all of those. And what the implication of that is that you're trading resolution and speed at all times. With that, I finished the 15th lecture, and we only have one more to go. In many ways, that's my favorite technique. That's the last one to come, structured illumination microscopy. And it was invented really by this man here, Mats Gustafsson, who was a real genius, who in my opinion would have been one of the worthiest winners of the Nobel Prize, but unfortunately he wasn't able to, because he died tragically far too young of a brain tumor at the age of, before he was 50, I think. And but the technique that he came up with is in many ways the most exciting, because it is very compatible with biological samples. The resolution is intermediate between the last two, but it is much, much faster to image, and sort of it seems to have the right balance of resolution and speed to be very useful for many biological experiments. And with that, thank you, and I see you in the last lecture.